Logic helps us communicate precisely. It helps us say what we mean and understand what others mean, including professors, textbook authors, and our colleagues at work. It is useful for writing clear program specifications, which is an essential part of software engineering. And it helps us understand the specifications that other people have written. Logic can help us when we are making database queries. It also helps us when describing circuits and understanding their properties. A proposition is a statement that is either true or false. 2 plus 3 equals 5 is an example of a true proposition. 1 plus 1 equals 3 is an example of a false proposition. Consider the statement, for every non-negative integer n squared plus n plus 41 is prime. This statement is false, but is hard to tell just by looking at it. In fact, n squared plus n plus 41 is prime for all integers n between 0 and 39. But 40 squared plus 40 plus 41 is equal to 41 squared, so it's composite for n equals 40. Thus, the statement is false. The statement, every even integer greater than 2 is the sum of two prime numbers, is known as Goldbach's conjecture. It is unknown whether this proposition is true or false. Some sentences in English are ambiguous, so it may be hard to tell whether they are true or false. Here are 3 examples. Pause the lecture and before continuing, try to give 2 different meanings for each of them. The statement, you may have cake or ice cream, when said to a young child, usually means the child may have either cake or ice cream but not both. When said to an adult, it usually allows the possibility of the adult having both cake and ice cream. Suppose I said, if you can solve any problem in the course, then you will get an A. I mean that if you can solve every problem, then you will get an A. But it can also be interpreted to mean that you will get an A if there is one problem that you can solve. Finally, consider the sentence, 2 sisters reunited after 18 years at a checkout counter. One interpretation is that the sisters met at the checkout counter after not seeing one another for 18 years. Another interpretation is that they reunited after one or both of them spent 18 years at a checkout counter. The ambiguity of natural language is one of the reasons that logic is used throughout mathematics and computer science, and one of the reasons it is not used in politics. Various words in English are used to create new propositions from existing propositions. Some examples are or, and, not, and implies. We can specify the meaning of these words using a truth table. We'll use Boolean variables such as p and q to denote arbitrary propositions. These are variables that have only 2 possible values, true and false. The MIT book denotes these values by the letters T and F. The course notes use 1 and 0 to denote them. In a truth table, there is one column for each combination of Boolean variables we are considering. The leftmost columns are for all the Boolean variables that appear in these combinations. There is one possible row for each possible setting of the Boolean variables. For any proposition P, the negation of P is true when P is false, and it is false when P is true. It is specified by this truth table. The negation of P is written as not left bracket P right bracket in the MIT book. In the course notes, it is denoted by negation symbol followed by P. The negation symbol is a horizontal line with a short vertical line descending from its right side. The negation of P is also written in a number of other ways, for example as a tilde followed by P, or as a P with a bar on top of it. Note that not P has the same sequence of entries in its column of the truth table as P does. In this case, we say that P and not P are logically equivalent. For any 2 propositions P and Q, the conjunction of P and Q is true when both P and Q are true, and false otherwise. It is written as P and Q in the MIT book, and as P wedge Q in the course notes, where the wedge is an upside down V. It is also sometimes written as P ampersand Q or P dot Q. For any 2 propositions P and Q, the disjunction of P and Q is true when P is true, or Q is true, or both are true. It is written as P or Q in the MIT book, and as P v Q in the course notes. It is also sometimes written as P plus Q. For example, consider this sentence, you may have cake or you may have ice cream. If said by a logician, it means that you can have both. For a logician to say that you can only have one of them, they must use exclusive or instead of or. For any two propositions P and Q, P exclusive or Q is true when P is true or Q is true, but not when both are true. The exclusive or connective is written as XOR, or as a circle with a plus sign inside. We say P exclusive or Q, or exactly one of P and Q. From this truth table, we can see that not P or Q is logically equivalent to not P and not Q. This is because the fourth column and the last column have the same sequence of entries: true, false, false, false. Likewise, not P and Q is logically equivalent to not P or not Q. These observations are called De Morgan's laws. Consider the piece of code at the top of the slide. Let A denote the proposition x is greater than 0, and let B denote the proposition y is greater than 100. Then we can rewrite the condition as A or bracket not A and B close bracket. From the truth table, we can see that A or bracket not A and B is logically equivalent to A or B, since the third and last columns have the same entries. This means that we can simplify the code at the top of the slide to the code at the bottom of the slide without changing its meaning. A proposition involving many variables can be difficult to write in a simpler form. However, this problem is important. It can be used to increase the speed of programs and to design circuits with fewer gates. It can also help to produce chips with fewer components, which are cheaper to manufacture, more reliable, and consume less power. For any two propositions P and Q, P implies Q means if P is true, then Q is true, as the last two rows of the truth table show. But what about when P is false? In this case, P implies Q doesn't say anything about whether Q is true. So no matter what value Q has, P implies Q is true. For example, suppose I said, getting perfect on the final exam implies that you will get an A in the course. If you get perfect on the final exam and I give you an A, then I told the truth. If you get perfect on the final exam and I give you a B, then I lied. However, if you don't get perfect on the final exam, I might still give you an A, or I might give you a lower grade. In either case, I told the truth. P is called the hypothesis or antecedent of the implication P implies Q, and Q is called the conclusion or consequent of the implication. The implies connective is also written as a line with an arrowhead at its right end, or as a double line with an arrowhead at its right end, or with the symbol used to denote superset. As you can see from this truth table, P implies Q is logically equivalent to not P or Q. Thus, P implies Q is true when P is false or Q is true. There are many ways that implication is indicated in English. The next three slides are particularly important for those of you who are not fluent in English. The first example is, getting perfect on the final exam implies you will get an A in the course. You get perfect on the final exam is the proposition P. You get A in the course is the proposition Q. The second example is the sentence, if the list is empty, then the search is unsuccessful. Here, the list is empty is the hypothesis P, and the search is unsuccessful is the conclusion Q. Next, consider the sentence, if the input is positive, the program halts. In this example, the input is positive is the hypothesis, and the program halts is the conclusion. The square brackets around then indicates the word then is optional. Sometimes if appears later in the sentence, such as in the program halts if the input is positive. In this case, the input is positive, which is the part immediately after the if, is still the hypothesis P, and the program halts, which is the part before the if, is the conclusion Q. The word only immediately preceding the word if changes its meaning. For example, in the sentence, the search is successful only if the list is non-empty, the hypothesis P is the search is successful, and the conclusion Q is the list is non-empty. The words when and whenever act the same way as if. In the sentence, when the robot detects an obstacle it turns, the hypothesis is the robot detects an obstacle, and the conclusion is the robot turns. The same is the case for the sentence, the robot turns whenever it detects an obstacle. Likewise, the word only immediately preceding the word when changes its meaning. For example, in the sentence, the search is successful only when the list is non-empty, the hypothesis P is the search is successful, and the conclusion Q is the list is non-empty. And in the sentence, only when the network is connected will the broadcast be successful, the hypothesis P is the broadcast is successful, and the conclusion Q is the network is connected. In the sentence, having a good initial value is sufficient for the method to converge. The words is sufficient for mean the same as implies. So the hypothesis is the method has a good initial value, and the conclusion is the method converges. These are also the hypothesis and the conclusion in the next sentence. For the method to converge, a good initial value is enough. The word necessary indicates an implication in the opposite direction. For example, in the sentences, at least 40% on the final exam is necessary for passing CSC240, and to pass CSC240, at least 40% on the final exam is necessary, the hypothesis is you pass CSC240, and the conclusion is you get at least 40% on the final exam. Finally, in the sentence, successful message receipt requires sending an acknowledgement. The hypothesis is a message is successfully received, and the conclusion is an acknowledgement is sent. So, this sentence means that if you successfully receive a message, then you must send an acknowledgement. Not Q implies not P is called the contrapositive of P implies Q. It is logically equivalent to P implies Q. Q implies P is called the converse of P implies Q. As you can see from the truth table, it is not logically equivalent to P implies Q. The converse of an implication is the original implication. What about the contrapositive of an implication? The contrapositive of not Q implies not P is not P implies not Q. If we simplify this by replacing not P by P and not Q by Q, then we get back the original formula P implies Q. For any two propositions P and Q, P is equivalent to Q means that P is true exactly when Q is true. Other ways to say the same thing in English are P if and only if Q, and P is necessary and sufficient for Q. IFF is an abbreviation for if and only if. This connective is also written using a line with an arrowhead on each end, using a double line with an arrowhead on each end, using an equal sign, or using an equivalence symbol, which is like an equal sign except that it has 3 lines stacked vertically instead of 2. Recall, when we say that two propositional formulas A and B are logically equivalent, we mean that they have the same sequence of truth table entries. This is the same as saying that all truth table entries of A if and only if B are true.